All right, so we are kicking off section 6.2 here. We are talking about formalizing what we're going to end up calling the definite integral, but what we're really doing is trying to extrapolate what we've learned about finite sums, estimating or approximating the areas underneath of curves with finite sums or rectangles, a finite number of rectangles, and extrapolating that to an infinite number of rectangles so that we can get the actual area underneath of a curve, all right, the exact area underneath of a curve. So this beginning part here is a proof, but before I show you the proof, what I need to do is remind you of summation notation very briefly. Because even if you had this in pre-calc, it's probably been a while. So real quickly, this is summation notation. This is in uppercase sigma right here. And all I have is a very simple summation rule, which is just k squared. And the way that this is going to work is it's going to take whatever your starting value is at the bottom, and then we're going to go by ones here to create a sum, which will have 4 terms in it. 5 terms. All right, so in order to write the sum out, it would be 1 squared. So we'd plug in 1, and then we would plug in 2. So it'd be 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay, so that's how the summation notation works. You have some sort of rule here to the right. You have the starting value here at the bottom, and then the ending value here at the top, okay? And then you could calculate what this sum was. So it's a short way to write sums, all right? So that's summation notation. It'll be useful here in a second. Let's jump to this graph, which a PDF of this is posted. If you want to print it off, it's going to make this lesson a lot simpler, and it'll save you some time. So what I have in this graph is obviously the xy axis. I've got a function, an arbitrary function, y equals f of x. This one happens to look the way that it does, but it doesn't matter what kind of function we start with. Then what I've done is I've drawn an arbitrary number of rectangles into the function. All right, so I'm starting this interval at a. A is going to be x sub 0, the first x coordinate here. That's a. And it's going to go all the way to b, which is the ending of the interval. So just like we've been looking at finding approximating areas underneath of curves from a starting point to an ending point, it's always been given. That's my A and my B here. Then I say arbitrary number of rectangles because while we can count the number of rectangles that I've sketched here, obviously, what I'm trying to do is set this up in a way that will scale to a general formula. I'm trying to keep things as general as possible so that we can arrive at a rule. Okay, so this is a proof, right? That's what I'm trying to do, is deduce a formula or a rule for you about finding the areas underneath of curves. Okay, so what I've got here is I've got x sub 0. That's my first x value. And then I have every rectangle. These the width of each rectangle is the same all the way through. And then I'm calling that first distance here, the first width, x sub 1. And then the next coordinate here is x sub 2, x sub 3, x sub 4, x sub 5, and so on, all the way down to you get to the last subinterval, which is x sub n. The one before that will be the x sub n minus 1 interval. All right, and then x sub 7, and do I have these twisted around here? Where's that? Just a bad 6. That's just a bad 6, I think. All right, so that's how we're keeping this arbitrary. Yes, there are 7, 8, however many rectangles there are, but we're trying to keep this as general as we can. Okay, so I've got that set up there. I've got these rectangles sketched in as using MRAM, although it doesn't matter. We could do this with LRAM or RRAM, but I just happen to use MRAM. This first point here is going to be located at C sub 1, comma, f of C sub 1. Now, C sub 1 represents the midpoint of the first rectangle, of the first subinterval. All right, so this right here is C sub 1. And you can see C sub 2 is here, all right? And then if I wanted to find the area well, actually, back up 1 second. So that will continue on all the way to the end. At the end, we will have C sub n, which would be the last subinterval. And then the height of that rectangle would be f of C sub n. Just like over here, if C sub 1 was 2, the height of this rectangle would be f of 2. Okay, so that's all set up generally. You can kind of see it visually there. If I wanted to find the area of the first rectangle, this is what I would do. I would just want the width times the height, right? Well, what is that? Well, we can figure that out. The width of this subinterval here is going to be whatever the distance is from x sub 0 to x sub 1. All right? That is and it's the same all the way throughout, right? The widths are all the same. That's how I built this, this picture. So that distance is the change in x. And what we're going to do is call that delta, that means change in, x sub k. All right? And that width is going to be multiplied by the function height at c sub 1. Okay, so the height of this rectangle is f of c sub 1. The width here is going to be delta x sub k, right? All right, so let's write that down. In fact, you know what? Let's, well, that'll be okay. So I'm going to leave myself some space, and down below here, I'm going to write the sum of all of these rectangles, okay? So the first rectangle is going to be f of c sub 1 times delta x sub 1, because that's just the change in x at the first rectangle, and that's why I hesitated a little bit earlier. We should probably just keep this as x sub 1. Okay, then the area of the second rectangle here would be delta x sub 2 times f of c sub 2, right? And that will just keep going on, okay? So n generally, but 1 for this first specific rectangle. So my apologies on that one. So this is the first rectangle. Plus the second rectangle. Well, the second rectangle we just wrote out, it will be delta x sub 2, so that's the change in x at the second interval. And then times the function height at the second interval. So that'd be f of c sub 2. So, so let's write that down. So f of c sub 2 times delta x sub 2 plus, and I'm getting kind of tired of writing this over and over already. Again, this is the second rectangle, just to be clear. That's the second rectangle, but I'm going to put dot, 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 and then I'm going to go all the way to the last rectangle. What's the area of the last rectangle? Well, you might pause and think about that for a second, but I'm going to give it to you now. So the area of this last rectangle is going to be the height of it, which is f of c sub n, times delta x sub n, whatever the width is at the end here. So plus, so we'll write that out. So it's f of c sub n times delta x sub n. All right, now we can't write this out for every single one of them. Or for every single problem, right? This would be completely obnoxious. And not only that, we don't want to write it out, but also we ultimately are going to want an infinite number of rectangles. So let's use some mathematical notation to do some work for us so that we don't have to write this nasty summation out every single time. What we're going to do is we want to sum a bunch of rectangles, and all of these rectangles are going to take this form. The function located at c sub k times delta x sub k. So let's see if that fits the pattern. You can see there's 1 here, and then 2 for our rectangles, and then the next one would be f of c sub 3 times delta x sub 3, and so on all the way down to n. We're going to let k start at 1. You can see then if I plug in 1 for k, I get the first rectangle, and then it will go up to 2, the second rectangle, and so on. And we're going to let that run all the way to the last rectangle, which is n. Okay, so that's going to be our sum. All right, and we'll write that as S sub n. This will be the sum of n rectangles. All right, where n is the number of rectangles, and so you can see that n is the number of rectangles, and k is your index, which is just tells you which rectangle you're trying to compute. Adds them all up. All right, this is called. That's not a good star. This is called the Riemann sums for f on the interval from a to b. Okay, so this is the mathematical general notation for what we did, what you've already done, right? You've added up a finite number of rectangles, but it's written in a specific way so that we can extrapolate it to taking an infinite number of rectangles. So let me show you what I mean by that. I did not leave myself space, so I will flip this over and we'll write this out. Okay, so this leads us to what is called the definite integral of a continuous function. Okay, so what we're going to do is we're going to take this expression and we want an infinite number of rectangles. So the way that we're going to represent that mathematically is using limits. Limits are a way that we can describe values at infinity. So what we'll do is we'll let n go to infinity. So we'll take the limit as n approaches infinity of that summation from the previous page. So where k is equal to 1 and n is the top level and the last rectangle. And then we'll take f of c sub k times delta x. And because I'm taking an infinite number of them and delta x is always the same, I don't need to actually keep the index on it. So you'll notice that here I did keep the k on it. It's actually not really necessary because delta x, the change in x, is the same in every spot. So we'll just set that as delta x. And that is the definite integral of a continuous function. Now, this notation is obnoxious, all right? So mathematicians simplified this to what's called integral notation, which you've actually seen a version of this before when we were doing antiderivatives. But the definite integral looks like this. It has the integral symbol, which is actually an elongated s, okay? And then I'm gonna write it in and then I'll describe each part. So we've got a at the bottom, b at the top, f of x dx, okay? So a is the lower bound. All right, b is the upper bound. And these are from the picture. So over here, we started with a as the lower bound, b as the upper bound. That's how those factor into this. F of x is called the integrand. That's the function that you are trying to, a and d, that's the function that you're trying to find the area underneath of, or between that and the x-axis. This variable right here, this x, this is called the variable of integration. Okay, the variable of integration. Right? That's really important to understand because this variable has to match whatever the function is. That'll become important later on. This entire thing is read as the integral of, that should be, I got ahead of myself. This is the integral of f of x from a to b. Okay. So there you go. That's the definite interval of a continuous function. We are going to apply that in a number of different ways going forward, but I just wanted you to have that the proof of that, all right? And I want to say one more thing, and then I think we'll end this video, and the application of it we will put into a different video just to keep each one manageable. So in terms of time, one last thing I want to say. This dx here, you might be thinking, well, where does that come from? It's because essentially you've got this piece here becomes the integral, right, from a to b, and this represents the infinite number of rectangles. The f of c sub k, that becomes the f of x pretty clearly. Delta x becomes dx because delta x is the width of the rectangles, and when we take an infinite number of rectangles, we are letting delta x approach 0. So delta x is going to get infinitely close to 0, but not actually 0. And the way that we represent that in calculus is with the differential, dx. Okay. It has the same sort of meaning in differential notation, like dy dx when you take a derivative. If you may or may not remember, but what we were doing with derivatives is we were letting that secant line get infinitely smaller, so that the gap between the a and b of the secant line, if you will, approached 0 but wasn't actually 0. Because if it was actually 0, it created a divide by 0 error. If it was infinitely close to 0, then we could still work with that mathematically, and it gave us the slope of the tangent line, right? So that's it for proving the definite integral of a continuous function on a given interval.